today I'm going to be talking about quantum light matter interfaces. So the idea is that I'm going to give you a bit of an overview of some of the recent work that I've done, as well as some of the upcoming work that we're starting up here in Illinois. So until last fall, I was at the Army Research Lab in Maryland and kind of in a superposition with the Joint Quantum Institute at the University of Maryland before coming here for the fall semester. So just to get everyone on the same page of what we mean when we talk about quantum information systems, even though this is IQUIST and we all have our own ideas maybe of what it is. We want to start with, we want good qubits. So what makes a good qubit? Something with a long coherence time, so that means strongly isolated from its environment, and something that we have the ability to prepare and read out with high fidelity. For any kind of quantum information processing, whether it's a kind of circuit model of quantum information processing or a cluster model of quantum information processing, we need the ability to entangle our qubits together, either using entangling gates or by preparing entangled states. And then finally, if we want to connect any quantum systems together that are separated by any distance that isn't inside the same cryostat or vacuum chamber, we need to be able to do some kind of quantum networking where we share entanglement between spatially separated nodes. Now, you might have realized from the title of my talk that I'm going to talk about using photons to do basically all of these tasks, hence quantum light matter interfaces. So why would we want to use photons for this? So first of all, for any kind of quantum networking, we basically have to use photons. So only optical photons can carry quantum information at room temperature. Nothing else can really carry a qubit across some kind of room temperature for over any distance. They have excellent coherence properties, so virtually nothing decoheres photons. They travel. We have commercial optics that allow us to encode and measure them, so we have relatively easy ways to encode and measure photons. And there's a sense of scalability. I can make lots and lots of photons at high rates for as long as I want. Okay, but photons are not the leading technology for quantum computing or quantum information technologies necessarily, and why not? That's because there's some problems with them. So the most basic problem is that making one at a time is hard. Natural light sources or lasers produce photons with photon number fluctuations, and what I need is something that produces exactly one photon at a time to make my flying qubits. Maybe bigger deals, two more problems with them. One is that they don't interact with each other. So there's no obvious way to entangle photons because there's no native interaction between them. And the other major problem with them is that they get lost. So in optical fiber, they get lost over long distances or longish times, and at interfaces between materials or between free space and some kind of waveguide, they also get lost. And these are kind of major issues that have held back photonic quantum information processing. So we're going to talk today about how to address all of these various challenges. So how do we make one at a time? Well, we develop quantum light sources, single photon sources. So these have been around for a while. Paul talked last week about single photon sources. I'm going to talk more today about some other kinds of single photon sources. What about the interaction? Well, we have two options here. Basically, we can either generate photons that are entangled with some matter qubit, and then use that matter qubit to have the interaction, to mediate interactions between photons. Or we can use measurement to induce effective nonlinearities in our systems. This is linear optical quantum information processing. In terms of them getting lost, we can store them in quantum memories. So we can make matter-based devices that can store single photons for some amount of time. We can make multi-photon entangled states, photonic graph states, that allow us to send logical qubits encoded in multiple physical qubits in a kind of quantum error corrected way that's robust with respect to at least some laws. And we can move toward putting everything in photonic integrated circuits on individual chips so that we don't have interfaces. Everything is all integrated in one, and we can reduce the losses on these chips. So today I'm going to be talking about trying to address all of these challenges using atom-like emitters. So one way to make single photons is to get a single atom or a single atom-like emitter, excite it, and it'll spit out one photon. If I use an emitter that has some spin and some long coherence time in it, then this is a natural way also to generate single photons that are entangled with the spin inside of the atom. I'm actually not going to talk about this next one today, but it is something I'm thinking about and working on, so we can talk about it later. Quantum memory, we can use many atoms or atom-like emitters to store single photons as collective excitations in these atoms. And we're going to talk about that. If this is not obvious, but if we couple one of our atom-like emitters to another system, this is one way to build up photonic graph states, multi-photon entangled states, to do things like that. And finally, if we use atom-like emitters embedded in solids rather than atoms in vacuum, we can move toward photonic integrated circuits. So I've been very careful to say atom-like emitters. And what do I mean when I say atom-like emitters? I mean either atoms in vacuum or something in a transparent solid that has an optical transition and a coherent low energy spin excitation, basically. So something that lives in a transparent solid and looks like an atom. And these are the things that we care about, and these are kind of two wide classes of atom-like emitters. So atoms in vacuum are great. Cold atoms have been studied for many years with great success in a variety of fields because they are these nearly perfect little spins. So each one is the same. They've got very, very long intrinsic coherence times. They're all naturally identical, but there are some drawbacks, especially for light matter interfaces. It's difficult to make compact devices. Usually cold atom systems have these massive complex apparatuses. There are limits on the number of atoms or the density of atoms that we can get in these vacuum chambers. So we can't really scale them up infinitely necessarily. And there's kind of an inherent difficulty in coupling them to photonic systems. So the big benefit of atoms in vacuum is that they're in vacuum. And as soon as I try and bring some waveguide or something near them, they're not really in vacuum anymore. And this makes it particularly difficult to efficiently extract light from atom and vacuum systems. Not impossible, just difficult. So solid state emitters, on the other hand, are not in vacuum. And because they're not in vacuum, they have some environment, and that environment has static variations from site to site. It has dynamic variations with charges and spins in the system. And this means that the transition energies, the optical transition energies of these guys tend to vary from emitter to emitter. There's excess decoherence and spectral diffusion processes in the system that cause us issues. They no longer all look the same, or even all stay the same over time. However, they do have a direct compatibility with integrated photonics. So typically these systems, we're talking cryogenic systems, so they don't require laser cooling, they just require money. And that makes the complexity of the apparatus much, much smaller. We can make high density compact devices with these. We can put everything on a chip and shrink it way down, and better for scalability. One of the major outstanding challenges in this field is that as these emitters get close to surfaces in general, that becomes a problem. So effects on the surface, charges on the surface, tend to degrade the properties of these emitters, though at a length scale that is much now shorter than the length scale at which, when I try and bring dielectric and other materials near my atoms in vacuum, I get this effect. So I've said up until now that the issues with photons, using photons for quantum information, I laid them out, the interactions and things like that, but I want to focus for a moment on the losses to really just convince you that this is the major outstanding problem with photonic quantum information, and it's not solved. So if I have any kind of photonic quantum network, it's going to look approximately like this. I've got a bunch of photons. They're going into some box. That box is filled with some kind of linear optics. And then I've got a bunch of detectors. This might be all on one chip. This might be over some very long distance. These linear optics might be other things, but it kind of looks approximately like this. And so I can steal an old picture about bosons for it, but it doesn't have to look exactly like this. And the problem is that if I only have some probability eta of getting my photon all the way through the system, if I try and scale this up, I'm exponentially bad in this probability eta, and this starts to kill me even at moderate photon numbers given kind of current efficiencies. So quantum memories and quantum repeaters, which are the things that we can build up for quantum memories, help because if we can separate this down into a bunch of lower loss segments, we can use our ability to store these single photons to at least convert this exponential into a polynomial, and also entangling a bunch of photons together to make photonic graph states made up of a bunch of entangled photons. Also helps because we can do kind of error correction. We can send logical qubits that are robust, at least with respect to some amount of loss in our system. However, if we can't even make the photons efficiently, this doesn't really help because all of this is about scaling as the losses scale and pretty much requires that you at least start with low losses and then you're mitigating the losses as you go along the way. And another big problem is that these photons, they all have to be the same. And we were just talking about atoms and atom-like emitters, and if we're going to use atoms or atom-like emitters to generate photons, if our atoms aren't the same, then the photons that they spit out are in general not the same. So this is kind of a separate issue, but one that's intimately tied up with how efficiently can you make single photons. So as an example of how we try and make perfect single photons efficiently, I'm going to talk about some recent work in collaboration with some folks over at Maryland at the Joint Quantum Institute. And in this case, we actually did use atoms in vacuum, so laser-cooled atoms in vacuum, highly excited Rydberg states to generate single photons. I am not going to describe this experiment at all. You're welcome to come talk to me about it or take a look at our recent paper, but for the purposes of this talk, we have a box and it spits out single photons. So here's our box, and on some clock, it spits out one photon. And so I've said that we need a source that produces exactly one photon in exactly one mode. And when I say mode, I mean the photon has to be at a particular frequency with a particular spectrum at a particular time in a particular transverse spatial mode, et cetera, et cetera, et cetera. And I have to know what that is, and it always has to be the same. So Paul talked again a little bit about this last week, but I think not everyone was here for Paul's talk last week. So when we characterize single photons, first, the way that we characterize that we only have one, so unlike a laser, which will spit out random numbers of photons, is we kind of do a relatively obvious thing. We take the photon and we try and split it in half and we see what happens. So we take our photon, we collect it into a single mode fiber here so that we're sure that we're in one transverse spatial mode. And then we go to a beam splitter, something that has 50% chance of the photon going through, 50% chance of the photon getting reflected. And we look at when we get clicks on these two detectors as a function of the time difference between those clicks. So these are detectors that just are kind of click, no click detectors. They click when there's a photon or one or more photons, and they do nothing if they see no photon. And we can see here that we get these coincidence counts where the detectors fire one clock cycle apart, which is about 5 microseconds in this case. And if we look though within a single clock cycle, we get basically no coincidence counts between the two detectors. If we zoom in, the blue here is the data. These are the coincidence counts that we're getting as a function of time delay within this central pulse. But this gray line on top here are the coincidence counts that we expect given the rate of false counts in our detectors. So that's the rate at which a real photon is accidentally coincident with a false count in the other detector. And we can see that our data basically lies right on top of that line, and we can show suppression of about a factor of 10 to the 4. So we are making exactly one photon when we're making a photon. What about this single mode question? So to determine if we're making photons in a single mode, we do what's known as a Hong-O-Mandel interference experiment. We take our photons and we randomly split them at a beam splitter here. And one of the arms of our beam splitter gets delayed by 1 clock cycle. So now you can see that 1/4 of the time, we're going to have 1 photon here and 1 photon here from subsequent pulses of our single photon box. And when we have 1 photon on one port of our beam splitter and 1 photon on the other port of our beam splitter, we can write down how beam splitters work. And we can see that if the photons are exactly the same, we get destructive interference between the term where both photons get transmitted and both photons get reflected. Only if we're creating identical photons at these 2 ports of the beam splitter do we get this cancellation. And we never should see a coincident detection on the 2 detectors out here after our beam splitter, if and only if the photons are identical. So we can do this experiment too. In this case, you can ignore the pink, but again, the blue is our data. When we zoom in, we again see hardly any coincident counts when we are looking within the same shot cycle here. Again, the gray is our background. This time we do have a little bit of excess over our background. Our photons are 98% identical. Finally, I didn't show it, but we can also simply extract the probability of a photon making it from our box through our single mode fiber, through all of our other filtering optics that ensure the, say, polarization of it, and onto our detector. And that gives us our efficiency for our source. So now we can plot up, and the whole point of all of this was to show you this plot, basically. We can plot up some of the best sources around in terms of their absolute efficiency. So this is the source that Paul talked about last week, as well as the fidelity. So the fraction that are correct, the fraction where we have exactly 1 photon and exactly 1 mode. We're the purple up here, Paul's over here. Basically, the point is this plot is very depressing. Efficiency is on a log scale, which is not what you would want. You would really want everybody close to 1. Fidelity is on a linear scale, which is also not what you would want, because you would want everyone close to 1 up here. And it turns out this is still a big open problem in single photon generation. And I'm not pointing it out here, but it turns out we've got the same problem when it comes to things like quantum memory, in that making efficient quantum memories is kind of just as bad in terms of the state of the art today. Okay, so that was a quick aside. And we're going to jump back here just to remind you some of the important factors in dealing with loss. Interfaces are lossy, so what we did with this cold atom system is we just put everything in free space and we had no interfaces, which is good for now, but probably not long-term great. Long-term, you probably want to put everything on chip to reduce interfaces. And you want your chip to be made out of some kind of good photonic material, so something that really transmits photons. Which unfortunately means maybe not silicon. Long distance transmission is also very lossy. This is a problem. So quantum memory, efficient quantum memory is something that we need. On-chip waveguides are much, much lossier than long distance transmission. And so if I'm putting everything on chip, I even need kind of relatively short quantum memory storage of my single photons on my chip, and that can be useful. And this is really what drives us toward wanting to move maybe away from atoms in vacuum and toward atom-like emitters in solids. Because all of these benefits of the atom-like emitters in solids really are kind of long-term the way that we're going to reduce losses in our photonic quantum systems, where losses are really, really paramount. Before I move on, was there a question? Are we good? Okay. So really quickly, we're going to do an incomplete overview of atom-like emitters in solids. So starting from scratch, if I were to design an atom-like emitter in solid, I would want it to be in silicon, because silicon is the material most like vacuum. We can make kind of perfect crystals of it. There's no nuclear spin if you isotopically purify it. But it turns out silicon does not like to host optically active emitters. Not that it won't, but there are many people have tried and many people have failed to get nice optically active emitters in silicon, and they're still trying, and maybe they'll succeed, but it's proven very hard. So, okay, not silicon, maybe 3-5 semiconductors, which is often the next step if you're starting with some kind of transparent material and silicon doesn't work. And this has a long history. So quantum dots in 3-5 materials have shown great success. A lot of the points on that graph that I showed were based on quantum dots in indium arsenide, quantum dots in gallium arsenide. They don't have great coherence properties, but they've gotten better over time. They don't have great inhomogeneity either. So in general, each dot looks a little bit different. They don't really have these long coherence times, but right now they may be the state of the art in terms of making photons from atom-like emitters, and they've proven very useful, and there's been a lot learned with these systems. So defects in diamond or silicon carbide, which is very similar to diamond, are another really interesting way to go. So there are lots and lots of possible defects here, which is interesting. Some of them have more or less issues of inhomogeneity, and some of them have better or worse spin coherence times and things like that. But there's been a lot of progress, especially in the nanofabrication front, because coupling these to kind of photonic integrated devices is very important. So this is a very active area of research that I'm also not going to talk about. And what I'm going to focus on today is what I mostly work on, which is rare earth dopants in transparent materials. So I'm going to talk about why, in particular, I think that rare earth atom dopants are particularly interesting.
Elizabeth, there's also been a couple of questions in the chat that I'm not sure.
Okay, I can't see the chat.
Oh, okay. So there's a question from Jim Eckstein. How do you quantify how identical two photons are?
Yeah, so we quantify it by measuring it using a Hong-Mandel interference experiment. So we do this with two photons here and here, here and here. And then we look at our rate of coincidences on the detector when we do this, and how many coincidences we get here is what our indistinguishability is.
Okay, and there was...
Maybe I could just ask a question.
Yeah.
If you had two pulses, and one of them had one wavelength more in that same interval of time that the pulse is happening over, but that would be the only difference. So there's slightly different frequencies. Would that have zero then identical aspect, or you know?
So this is an excellent question. It depends on how fast your detector is and how different they are in wavelength. So when you actually do this, you have to keep track of what the time width of your photon is, what the frequency width of your photon is, and what the frequency width of your other photon is, and what your detector is doing. So what's the temporal and spectral resolution of your detector? And your detector can act as a quantum eraser and erase, say, frequency differences if it's very fast in time. So this is a whole nother question, but it's well understood. I mean, it's easy to work out what it is. In this case, we didn't have that problem. We have actually another paper where we interfered these photons with photons from a totally separate experiment in a totally different building. And we were doing a little bit of quantum erasing by using detectors that were faster than the frequency difference of the photons.
Okay, well, maybe we can talk more about it later too.
Yeah, I'm happy to talk about that anytime, but I might get a little off track.
There was also one more question from Ophir. It's about the coherence length of photons.
Yeah.
Are they indistinguishable to 98% of the time when you integrate over the coherence length, or only within a small temporal window of the detection?
Thanks, Ophir. These photons that we made here are indistinguishable 98% of the time over the, well, we filter out a tail in software but they are indistinguishable 98% of the time over basically the entire pulse, which is this kind of microsecond, well, sub-microsecond looking thing in the center, really. Yeah, so we're not.
Yep, thanks.
Okay. All right, any more?
That's all.
That's all? Okay, great. Okay, we were rare earth dopants. Great, so now I'm going to talk about rare earth atoms and solids, my favorite thing. Okay, so why do we like rare earth atoms and solids? These are the rare earths. I like them because I'm really an atomic physicist at heart, even though I just told you all of the reasons why solid state emitters are better than atoms. But rare earth atoms are the most atom-like of any solid state. So this is because of special weird lanthanide chemistry. So I'll teach everyone a little tiny bit of chemistry. The valence electrons, the active electrons in the rare earth atoms are 4f electrons here. This is a plot of the radial wave functions of 4f, the 5s, and 5p. The 5s and the 5p are full in the rare earths. This is just a schematic kind of showing exactly the same thing. The 4f electrons live inside these full 5s and 5p shells. So these electrons don't really care what's going on out here, which is the crystal that they're living in, because they're shielded by these full orbitals. This means that even at very high densities, these atoms can retain their atom-like behavior. You take a free atom, it looks like whatever it looks like. You put it in some solid, it still kind of looks the same because it doesn't really notice the environment. In addition, they have very, very long coherence times. So their optical transitions have kind of millisecond scale coherence times, which is interesting for doing quantum memory. Their spin transitions, so they have nuclear spin transitions that have been shown to have coherence times as long as hours, which is very exciting for doing long-lived quantum memory type things. Basically, all of these are things that you want. So making efficient, identical single photon sources, you really want something that doesn't depend strongly on its environment. Making good quantum memories, you want things that are at high densities. Doing almost everything if they can be hosted in many different solids, and this has to do with the fact that they don't really care about their environment that strongly. That means that I've got lots of options for optimizing my system based on other metrics. I don't have to live in diamond. I can live in lithium niobate or glass or whatever I like, but maybe silicon. And these long coherence times are great for efficient long-lived quantum memory. So why doesn't everyone use rare earth atoms and solids? I mean, I don't know, but there are some reasons. So there are some challenges with them. So first of all, they look approximately like this. We have some free ion spectrum here. We go into a crystal field and we lift a bunch of degeneracies on our electronic spin in these states, and then for the most part, or at least half of them, have nuclear spin, and we have these long-lived nuclear hyperfine transitions. So first of all, these optical transitions that we're interested in here are very, very narrow and slow. They are not allowed in the free ion. They are 4f to 4f transitions, which are not allowed in the free ion. They're only weakly electric dipole allowed in the crystal because of the crystal field, doing a bunch of stuff and mixing a bunch of stuff in. So they're very dim emitters. So unlike, say, an NV center in diamond, where I can just put a microscope on top, send green light in, get red light out, and see a single one with a microscope, these guys emit kind of too slowly to see one at a time just on its own. In addition, they've got all this junk in between. So all these levels in between that make them not look like rubidium in a world where atomic physicists want everything to look like rubidium. Rubidium doesn't have this stuff in the middle. There's a bunch of radiative transitions in between so that we don't have any cycling transitions or anything like that. In addition, I said they're not that sensitive to their environment, and that's true. On an absolute scale, the environment causes shifts that are small, but on a relative scale, because we're starting with such narrow lines, the shifts are many line widths of each atom. So even these small variations cause shifts of many line widths of the atom. And unfortunately, the really, really long-lived nuclear transitions, in at least some of these splittings here are smaller, are very small, and are smaller than this overall spread of the optical energy, and it makes these super long-lived transitions we would like to use, it makes them unresolvable in the bulk, in the whole crystal, if we look at all of the atoms. Okay, but we can overcome these challenges, and we're going to. So, given the weak emission, we have two options. We can couple the atoms to resonators or waveguides to enhance the emission, make it faster, or we can use lots of atoms, which is the dumber way to do it, but often the way we want to do it. So take the first one first. So, okay, I'm going to tell you first about some work that I did back at Maryland before I came here. That's ongoing in collaboration with Edo Waks at Maryland. So let's remember that putting things on chip was something we wanted to do long term. And in addition, kind of using good optical materials was important to us. It was a way that we were also going to look toward making better on-chip devices, was by using materials that have these nice optical properties. And lithium niobate is one of those materials. So lithium niobate has a long history in classical optics. And in fact, rare earth doped lithium niobate has been used for quantum memory, but only with kind of big waveguides that don't do much to enhance that light matter interaction. So it guides the light, but it doesn't really do you much good in terms of the fact that the atoms are weak. And so what we did is we looked at thin film lithium niobate, which enables better nanofabrication techniques for making smaller waveguides. So we make smaller waveguides, there's more light confinement, this does increase the light matter interaction, and there have been some really nice demonstrations of making these waveguides pretty low loss. And so we made some of these devices. So these were our first devices. We took thulium-doped lithium niobate on insulator, and we made little waveguides out of it. And what we did is we wanted to know, when we do this smart cut technique to make this thin film lithium niobate to get these tiny little waveguides. Does doing that and doing all this fabrication, does it degrade all of these nice properties of the rare earths that we like? So we took a look at what happened to the thulium atoms in our system. The optical absorption was the first thing. So did we broaden out the spectrum? Did we give bigger shifts to the atoms, bigger than we had in the bulk? So what we have here is we have the optical absorption as a function of wavelength in our bulk crystal, and so we have something that's several nanometers wide. In lithium niobate, this broadening is pretty big. And then when we look at the same thing in our waveguide, we have an overall filter, which is what's killing the absorption out here, or the transmission out here, sorry. But we can see that our feature here is at the same place and has the same width as it did in the bulk, so that's great. We can also look at the optical lifetime and the width of the photoluminescence. So the width of the photoluminescence should be similar to the width of the absorption here. And the optical lifetime is telling us, have we done something nasty in terms of phonon coupling or something else that's causing our emitters to decay faster? And the answer is no, we get exactly the same optical lifetime. We get basically the same photoluminescence width between the bulk and the waveguide. And then finally, and maybe importantly, we start to look at some of the spin properties. So in this case, we burned spectral holes, which is to say we came in with a resonant laser and we modified the population in the ground spin states in our system, and then looked at how that decayed and also how wide it was. So we come in, we burn a spectral hole like this, and we look at the depth as a function of the detuning. So we were making spectral holes that were sub-megahertz. That puts a limit on the coherence properties of our spin states, which is reasonable. And we also looked at the decay of that spectral hole, and that puts a different limit on the coherence properties via the lifetime of the spin. And it turns out we saw this is basically the same as in the bulk. We saw no substantial differences compared to the bulk, and so now we need to really directly investigate coherence, spin echo and photon echo in the system, and do more than just make waveguides and start to make optical resonators in the system. So this is a really exciting potential way to go to integrate this system. This work is happening at Maryland. Here, I'm starting up a new project, also looking at putting rare earths into resonator structures. So what we're doing is we're fabricating microsphere resonators, starting with commercially available rare earth doped fiber. So this is a common material for making lasers. And eventually we want to move toward using individual atoms connected to these very high quality factor resonator modes in these microspheres as a source of single and entangled photons. The idea behind this is that because we're starting with silica with rare earth doped fiber, we can get extremely high Q resonators because the quality factor of these resonators is going to be set by the losses in the resonators. The loss is very low in silica at telecom, and so these can have kind of record high quality factors. And these modes, which are kind of more micro scale than nanoscale, are well matched to the propagating mode in, say, a tapered optical fiber that we can bring close and extract photons into. And so this is good for efficient extraction, which is a challenging problem with nanophotonic structures. Getting the light in and out efficiently is challenging, and this is one way to do it. So we've started working here on learning how to make these resonators and making our first ones. So we've been working with Gaurav Paul. I think this is actually a picture of his setup, but I've got a student who's been spending some time with him and has made some of our first resonators here and has started to characterize them this year. So this is really exciting, and I'm excited about moving forward with this project. So back to our favorite rare earth atoms. So we said we can couple them to waveguides or resonators to deal with the fact that we have this weak emission, or we can use many atoms. And this is the standard technique for doing things like quantum memory, so storing single photons in an ensemble of atoms. But now, if we're going to do this using many atoms thing, we have the problem that we have to deal with these small site-to-site variations between our atoms. So it's maybe not obvious, but this fact that we cannot resolve the long-lived nuclear hyperfine states over the variation in the optical transition energy from atom to atom gives us a trade-off between the efficiency of our quantum memory and the storage time of our quantum memory. Because the efficiency of our quantum memory depends on the optical depth of our system, which depends on how many atoms we have. And the only way we can access the really long-lived spin lifetimes, coherence times of these hyperfine states is by selecting out a subpopulation of our atoms where we can resolve them, only a narrow spectrum of the atoms that are available to us. So either we can resolve these states and use them, but only with a small number of atoms, or we can use all the atoms and we don't have access to the long-lived states. So we either can have efficient or long-lived storage because of this problem. This is the schematic of what any kind of spin state storage quantum memory looks like. I have a photon and it comes in. I've started with all of my atoms optically pumped to a particular state. Yes, I could, in theory, just cool the thing down so all the atoms fall down here, but I don't have cryostat cold enough for that in these kinds of systems. That's inconvenient for a variety of reasons. And if I can't resolve these states, because the difference in position of this level, say, varies by more than the splitting of these levels, then I can't optically pump. I need something that looks more like this in order to optically pump these states. So we are starting and continuing from Maryland and starting up here a couple of projects to address this challenge, so address the challenge of optical pumping. So one, we are employing new techniques in commercially available materials where we can resolve this transition under certain circumstances to try and optically pump, which has proven very difficult to date. And two, we're investigating new materials with properties that allow them to be optically pumped, namely smaller optical inhomogeneity. So the status of these projects, so the first one is these commercially available materials like erbium, doped yttrium orthomanidate. We can, at moderate magnetic fields, which we get by putting a permanent magnet in our cryostat, resolve the spin transitions in this system. We cannot yet optically pump because in erbium, the lifetimes of these spin transitions are too short compared to the very long optical lifetimes. It's trying to fill a bucket with a hole in the bottom. When you try and optically pump, they just fall back up very quickly. But we are going to go to lower temperatures to help with that system. And in the meantime, we're investigating four-wave mixing in this system, which is very similar to quantum memory. We have also started an exciting new project with Daniel Shoemaker here at Illinois to investigate new materials where, in fact, somewhat counterintuitively, we're going to increase the density of europium atoms in this case in order to increase their uniformity so that they're no longer dopants, but in fact they sit in every single site. And this should reduce the optical inhomogeneity because each atom now is in a more similar environment because there aren't these randomly placed dopants. And then we will be able to resolve the spin transitions in europium. And it turns out one of the reasons we're targeting europium is that it has the really, really long spin transition coherence times of hours. So this project has just gotten off the ground. I think this is a picture from Daniel's, one of their first growth efforts, which is exciting. So these are the things that we are starting here to try and overcome this issue. But in the meantime, back at Maryland, we knew that even though we were going to try and address this, we were going to be able to optically pump our system, we were going to still have the problem that no matter what we do, the line width of each atom is still going to be much, much smaller than the spread of atoms. Even if we can make that spread smaller, each atom is still some narrow little guy. And how is this going to affect our quantum memory protocols? And this is similar to, say, a Doppler broadened gas of atoms, but in a Doppler broadened gas of atoms, the Doppler broadening, which is causing the inhomogeneity, is also causing other things. It's also the source of a bunch of decoherence mechanisms due to transit of the atoms through the beam, collisions, and things like that. And here it's a little bit different because all it is inhomogeneous broadening. We don't have these other issues. And so what we want to say is, okay, can we pretend that we have effectively a homogeneously broadened system instead of an inhomogeneously broadened one, like we would like to do? And we decided to use electromagnetically induced transparency to ask this question, because it's kind of a ubiquitous quantum optical protocol that depends on the line widths of the optical and the spin transition of the system. And so the question is, if these are inhomogeneous line widths instead of single atom line widths, what happens to EIT? So EIT is a process by which I can send through a weak probe field into a medium that's nominally absorbing because I've got atoms here. But if I turn on a bright coupling field, then I open up a narrow transparency window for my probe right in the middle of what would otherwise be an absorbing feature. This is also a way to do a quantum memory. You can, in fact, store your probe field by doing this if you turn the coupling field off in the middle of the process. We're not going to do that. We're just going to study the properties of this EIT feature here. And I said we can't optically pump our system like this, but we can in a narrow region. And in fact, we can control the region that we do it in. So we use spectral hole burning techniques to control this inhomogeneous width. So what we do is we pump away all of our atoms in some region of spectrum. So we make this high transmission region here, which is a spectral trench, by scanning a laser field back and forth. And then we replace atoms in the middle of our spectral trench with by being careful about our laser frequencies. And we can control the width of this absorbing feature here. So these atoms have been selectively pumped to a particular state, only in a very narrow spectral region. In these other areas, we've pumped the atoms to some auxiliary state. So we need two states to do EIT. We need a third state to dump the atoms that we don't want. And then eventually we can't pump anymore because of the level structure of the system, and we get outside of our spectral trench and we have high absorption due to atoms that are just hanging out in every level. So we can vary the width of this feature. This is just how we measure the width of the feature. We scan our probe laser across it and measure the transmission. We can go from about 300 kilohertz, which is set by our laser line widths, and we can go up to about 2 megahertz, which is set by how wide we can actually make this spectral trench here. So the other knob that we have to turn is the intensity of this coupling field. So as a function of the width of that spectral feature that we made and the intensity of our coupling field, the Rabi frequency of our coupling field, we can come in with our probe laser, we can scan its frequency. If we don't have the coupling field on, we're just measuring the feature itself, the absorbing feature. That's the gray in the background in these two plots. So we've got one kind of wider one and one narrower one here. If we turn the coupling field on, we open up our transparency window. So those are the black lines in the two plots. And then we can measure both the visibility of our transparency, so how close to fully transparent it is, and also the width of our transparency window here. Now, it turns out we actually have another knob to turn in this, and that is, in fact, we can change the single atom line width of our excited state by using two different atomic species. So in fact, we did this experiment in two completely different cryostats, one with europium and one with praseodymium. And the reason we chose europium and praseodymium is first because we had europium and praseodymium, but second, because praseodymium has a 10 times wider line width than europium. And so if we're trying to check, can we describe our EIT only on the properties of the ensemble, or do we have to consider the properties of the atoms? Using these two species was very natural. And so what we did is we looked at the line width and the visibility of the EIT over a couple of orders of magnitude in our various parameters and for the two different systems. And we observed that our data collapses all in the same curve. So the visibility of the EIT, the theory fell off of this plot, but both species follow the same curve that we expect for the visibility as a function only of the ensemble properties. So the Rabi frequency of the control field and the width of that feature that we burned. And it doesn't matter if it's europium or praseodymium. And the same with the line width of the EIT. It falls along the same curve where there's some uncontrolled spin inhomogeneous line width that's different in the two species that we know about. But as long as we stay away from that, everything falls on the same curve as well. And this is very encouraging, that if we can develop a system that we can optically pump, a system where we can reduce the inhomogeneity significantly enough that we can do these kinds of quantum memory techniques, that we don't have to worry about the fact that the atoms still are a little bit different. And this is true for basically all solid state systems. Basically all solid state emitters have problems with inhomogeneity. And so we think this is a little bit widely applicable as well. So that is the end. Hopefully I've convinced you that efficiency is all important. Efficient single photons generation and storage is vital, and it's the only way we can scale up photonic quantum information processing. But it turns out it's also the only thing we have to do. If we can solve this problem, we can kind of solve all of the problems. And that in particular, rare earth dopants in solids are very promising as quantum light matter interfaces. And I told you a little bit about some of our new directions here at Illinois, in addition to the projects I talked about back from Maryland. And this is the picture of us before we moved from Maryland, and this is the picture in the lab space up here in Loomis very recently. So thanks a lot.
Thanks, Elizabeth. That was a great talk. Yes, now we have some time for questions. Feel free to post them in the chat, or if people want to just chime in, I think that should be okay too. And I think we also can have some time to chat if you want for discussion time afterward with Elizabeth in a kind of non-recorded setting.
Hey, Elizabeth.
Paul.
Paul, very clear talk as always. I really appreciate that. I'm wondering, what are the prospects for having bandwidths greater than 2 megahertz or something? I think that was the broadest one that you showed, right?
And so yes, in fact, there are. So I maybe didn't totally go over it, but there are methods for doing short quantum memories with broad bandwidth and high efficiency by storing directly on that optical transition and actually making use of this inhomogeneity. So gigahertz have been demonstrated, and there's no real reason you can't go bigger than that because you can get very large optical inhomogeneities. So that is one method. Now, these kinds of quantum memories that store on that optical transition are not great. They're very good right now. They're long-term not great because they have kind of fundamental noise floors that aren't that low.
I see. Thanks.
And there's a question from Jackson on the chat.
Okay.
How do you access the 4F core electrons of the rare earth atoms if they're being shielded?
Yes, thanks, Jackson. So that is the partially full shell. So it is the configurations of those 4F electrons that are all of the levels in the system up until you start to excite them to the 5D, which takes a long time. In the free ion, the 4F to 4F transitions are not allowed, symmetry considerations. But when you go into the solid, you're not in free space anymore. And now, in fact, your states are really admixtures of some 4F configuration with a little tiny bit of a 5D configuration that makes them very weakly dipole. And so, in fact, there are considerations of the exact site symmetry of your atoms in your crystal as to whether or not you've made the transitions you're interested in allowed or not, and things like that. So there's some group theory in there as well that I'm not going to talk about.
There's also a question from Mari Sunga concerning quantum memory. How many qubits are you talking about?
So the quantum memories that I'm talking about here are devices that basically just delay single photons. So it's a box, you send a single photon in, it comes out later. So it's up to you to encode your single photons as you want, and things like that. So some of these can be multi-temporal mode, so they can store chains of single photons and retain the ordering and the coherence between them on their way back out. Some protocols have less opportunity for that, but if you're in a solid, you can also imagine spatially multiplexing relatively simply as well. So I'm not really storing qubit states here. I'm storing individual photons that can carry qubits.
Mari says that makes sense. Also, Paul had another question. Can you comment on the heraldability of these Q memories, the quantum memories?
Yeah, they're not heraldable at all. They are just basically, boxes, single photon in, single photon out, which is why you really need the efficiency to get much higher. Or as we've talked about before, you need good photon non-demolition measurement, which is a whole other very difficult problem.
Any further questions? Paul says thanks. Okay, if not, maybe let's thank Elizabeth again. Yeah, if anybody wants to stay, we can have, I guess, a session for discussion. Sound good?
Great, thanks, Edgar.
Hey, Elizabeth, maybe I'll ask one more question as
Please
people are
do.
walking out of the room. In these, the thin film lithium niobate systems, first of all, maybe I missed it. Do you guys grow those? Do you get them from Marco or?
No, so we buy lithium niobate and then we send it to NanoLN, which is a company that does the smart cut process. So Gaurav was on earlier. It looks like he might have gotten off, but he's doing the same thing. So I think he's maybe using other techniques to thin the lithium niobate.
I see.
In the end, what you want is you want a thin layer of lithium niobate on insulator. Hundreds of.
Do you start out with a thicker waveguide and you basically shave it down then?
You start out with just a bulk crystal. You shave it down and then you write waveguides in it.
I see. So obviously you can get pretty high electric fields in those. Are those at all? I'm sorry, say again?
This is why Marco is doing this whole thing, right?
Yeah, right. The question is whether or not that can be useful for doing some sort of a Stark shift on any of these. And does that allow you to have some kind of control in some way?
Absolutely. I mean, these guys have, there's a Stark shifting it works. We can shift them around using electric fields. In fact, some of the earlier demonstrations of quantum memory in these systems did exactly that. They did gradient echo memory at all?
Yeah.
They did basically a version of that with an electric field that they switched instead of a magnetic field to demonstrate a quantum memory. So yeah, right, that's another very interesting way for this to go.
Yeah, very cool. Yeah, that's really interesting. We should think at some point about maybe again trying to couple our systems where we can have very fast reconfigurability on top of a long-term memory, a longer-term memory that you can provide.
Yeah.
But we still need someone to give us our quantum non-demolition measurement. Oh, we've been having some discussions, Eric and I, with Shuo Sun now in Colorado, who's looking into doing that kind of thing. And I don't know, maybe there's some hybrid scheme. I'm concerned this notion of just needing to have the efficiency be super, super, super high. The problem is not even your system. Even if you get your system super high, it's the fact that the person who handed you the photon accidentally lost some part of them because he wasn't very careful, or the fiber company wasn't very careful, or whatever.
Yeah, I keep trying to convince Trey that their Rydberg system that we use to make single photons can also be a non-demolition. I've so far been unsuccessful.
Well, maybe Jake.
Yeah, I mean, that's very different though. He doesn't do this. So this is not a like Rydberg tweezer thing. This is more along the lines of what
Mark Safford.
Bryce and-
Oh, I see. Yeah, collection ensembles. I see, because you need to have a high enough
It's an
density.
ensemble,
Yeah.
Yeah, we're just doing Rydberg EIT, but it's blockaded Rydberg EIT.
Got it.
So it's not so, well, it is a single photon source in our case, but it can be actually a single photon filter. Right, your probe pulse for your EIT comes in, but only one photon can get slowed down. So all the other photons scatter, one goes slowly through the medium and comes out the other end.
Well, that's a perfectly lovely single photon source potentially.
That's the only reason we didn't do it exactly that way in this is you make it slightly better by very, very briefly storing that one photon and then retrieving it, as opposed to just letting it through.
I see. Yeah, but if you can keep off the higher photon contributions, that's nice.
That's exactly what we're doing. We're just throwing away. We send in a pulse that's got tons of photons in it, all but one scatter, and then the one comes through.
Yeah, that's interesting.
That's how it works.
And then I guess if you want to store qubits, for polarization qubits, I guess you'd want to have two different ensembles, one for one component, one for the other component.
Yeah, convert yourself into time bin Q. There are a variety of schemes you can imagine doing for any of these to store qubits. If you can build one, you can build two.
So in the case for time bin qubits, is it necessary? I would imagine it's necessary that they be separated by more than this 1 microsecond, more than the one over the bandwidth, right?
Of the photons?
Yeah.
Or
Well,
quantum
of your memory, of your memory.
Of the memory, sure, but you can make these high bandwidth. So
With the optical, doing the direct transition.
you can do these short-lived short-lived multi-temporal mode, high bandwidth, efficient quantum memories.
Right. That's like also what Wolfgang Tittel does, for example.
This is exactly what Wolfgang does. That's what I'm talking about. Yeah.
And I guess there's no way to do the short-lived one and then to somehow swap it to a long-lived one.
Well, not without. I mean, this is this trade-off, right? So this is this. You either can take advantage of all of the atoms, or the long-lived transition of some of the atoms, and the sum is like 0.01% of all.
Right.
So you have no bandwidth. So you also lose bandwidth when you go, which I usually point out, but I forgot to this time. I forgot you were going to be here.
The talk was fabulous. I wouldn't have changed a thing.
But the trade-off is either high bandwidth efficient or long-lived.
Got it. Yeah.
Unless if we're successful though, we're solving that problem.
Right. It's interesting. It's almost like like a gain bandwidth product, but normally.
But it's not fundamental like a gain bandwidth product.
Right. Yeah. Well, that's why it's kind of odd that it comes up anyway. So there's another question in the chat, although you might have already kind of answered it. Wen Chao Zhu is asking, can quantum memory generally store the information of a qubit, which is superposition of two states? So
we leave that problem up to the user. So as a general rule, we try and develop a little box that can store your single photon, and it's up to you, the producer of single photons, to encode them in such a way that you've encoded a qubit.
Yeah, in particular, yeah, right. You can store a single mode.
Yes, and that if you're not storing a single mode, it's not a quantum memory.
Right.
Yeah. So we can either build two of them and split, store, recombine.
Yep.
We can do temporal qubits, but for the most part, we're not directly storing qubits.
Right. All right. Cool. Thanks again, Elizabeth.
Yeah.
I'm going to pop over to our other little lunchtime discussion here.
Yeah. All right. Let's see. So now I can see the chat. Maybe. All right. If no one else has anything, I'm going to hop off. Thanks, everybody.